Our guest storyteller today will share with us his experiences of being part of the Credible Sport team. In the spring of 1980, the Navy was called in to help Lockheed convert a C-130 Hercules so that it could take off and land in a very short space. Please join me in welcoming Mr. Lewis Renner.
Thank you. This, of course, took place quite a while ago. When I left China Lake, nobody knew where I was going, what I was doing. It was that secret. And I was gone for 3 months, and nobody knew where I was. It all started in April of 1980 when then President Jimmy Carter announced that an ongoing effort to rescue the hostages in Iran had gone disastrously wrong. And the aircraft never made it. We got some stories that the choppers got into a sandstorm and got knocked down. Almost immediately after, they started a follow-on program with the Air Force with a much more, well, very energetic program to go in and rescue the hostages. This time they selected the C-130, which was their workhorse type aircraft. But the problem was they needed to land it in a soccer field in the heart of Iran, and then turn it around and take it back off out of that soccer field, clearing the 30-foot high bleachers all the way around the soccer field. For a C-130, that's an absolutely amazing thing. The Air Force started with the program with Lockheed, and they were looking at JATO units. That almost went away right away because it took 58 JATOs to get it up out of there. At that point, the Navy was called on, and there was 2 of us from China Lake and 6 from Dahlgren that were called into that program. When I got the phone call from my ex-branch head, he said, "I can't tell you what this program is, but I think you would really be an asset to come help us, and would you like to come join the team?" I said, "Okay, that sounds good. What do I do and how do I get there?" He said, "There will be a call from the Pentagon to the station commander, and it'll come up the chain of command, and you'll be on an aircraft the next morning headed for Lockheed Georgia Company in Atlanta." Next morning, we were out, and then I got briefed when I got there, and then we really started to understand what the problem was. They said, "Well, the biggest problem is we want to take this C-130. You have to do the design, fabricate it, and do the testing, and we want it operational in 3 months. And everybody said, "Oh, sounds terrible, but sure, let's go." Because of the short period of time, we had to go with standard Navy rocketry, which we pulled rockets that were currently been in the fleet and were operational and had been qualified as usable on aircraft. We went with the standard Mark 56, which is a boost sustain motor, and those we ended up with 8 Mark 56s, 4 on each side, in 2 quad pods angled out and down at 15-degree angles. The biggest thing, of course, is we were doing pretty much just the rocketry. Lockheed was doing the retrofit on the fuselage and putting horsels and dorsals and added ailerons on the aircraft for greater stability and a lot better flight characteristics. The retro rockets, there was 8 retro rockets to stop it. And we'd gone through a pretty elaborate evaluation and had told them that there's just no way you can fire more. They wanted to fire them in the air to slow the aircraft down. And boy, you start looking at that scenario. And they said, you know, you cannot fire more than 4 of those in the air. And we don't even recommend that you fire any of them until you're on the ground. Well, as you'll see in the video towards the end, we proved our point. You can't fire all 8 retros at 30 feet in the air. And you'll get a really good video part on that. It'll show you exactly what we were trying to tell them, but they didn't quite listen. Several things that I'll cover that won't be covered in the video. First thing that we encountered is the Mark 56s being very, very hot exhaust plume. We fired some partials, 2 motors rather than 4 on each side, and just per chance, we happened to be back by the tail assembly. The horizontal stabilizer on that C-130 was a bonded assembly, and it was becoming unbonded from the heat from the rocket exhaust. So that was the next thing that we ended up having to be a part of and try to solve. We ended up with a paint-on material that back then we could still use asbestos. And so we had an asbestos material that was in a rubberized base that we were able to paint on the side of the fuselage and the horizontal stabilizer in the rear, and we're able to solve that. You only see that it's, I think, 2.5 seconds for the boost phase, and then a much longer sustained phase for the Mark 56. So that worked out really well, and the Air Force had some problems as we went along. They were able to solve their problems, and at the end of that 3-month period, sure enough, we felt we had an aircraft that was capable of going in, rescuing the hostages. The Lockheed was in the process at that time then of modifying the aircraft itself, adding all the extra horsals, dorsals, and extended ailerons. They were also putting gear inside because we were going in with 100 Special Forces troops and all their gear and equipment, so that when they landed, they had enough force to go in and take those hostages back and then get out of there. The biggest problem that we had was rocket motor exhausts. On landing, the retro rockets, again, turboprops do not like hot exhaust gas. So first test that we ran, we just fired the upper rockets, and we did a ground test, and sure enough, all 4 engines flamed out. So we had to adjust the angle so that the hot exhaust gases would go up and over the wing sections and not flame out our Mark 56, or flame out the turboprops. Then the other thing that, and boy, Lockheed just absolutely couldn't believe it. We said our 8 Mark 56s are going to supply 9 times the thrust that your 4 turboprops do. So you need to beef up that fuselage so we can get it up and out of there without breaking the fuselage in 2. And as you can see, you'll see in the video, that really worked out well. We were able to do that. On top of the 8 Mark 56s, we had outboard on the wings, rocket motors in case we had a Mark 56 that didn't fire. They would fire the opposite wing to correct yaw. A lot of things, and that was all computerized. So that, and then they told the pilots the bad news. Well, the other thing is we want to go into this field in Iran, but we want you to do it at night with no landing lights. So we're going to mount a forward-looking infrared, a FLIR unit, and you're going to be just looking at your FLIR landing this thing, going over this 30-foot obstacle at the high angle of attack, pulling up. And again, we had rockets mounted vertically on the fuselage. that as you flared, you had a really high loading on the wings, so we were unloading the wings with the vertical rockets. A lot of things that you don't think about going in, but they're there, and boy, all of a sudden you find, yeah, I got a problem. When we went down to Eglin to do the testing, to show you the priority that this had, when we went into the base commander at Eglin, he said, I've already got a call from the Pentagon. Do you want me to shut Eglin down? And we said, absolutely not. Boy, that'll tell everybody what's going on. So they put us out into a remote field at Eglin, and that's where we did all of our testing. Because we were at a remote field, again, we had Special Forces troops patrolling that remote field day and night, 24 hours a day, just to make sure we didn't have any intruders sneak up on us. And then we got to that point where we were doing the final fill-up tests, and sure enough, fortunately, we did the takeoff version first, and it is absolutely fantastic. You won't believe it when you see it. And then they came back around and they said, okay, we think we can do this, and sure enough, they fired all 8 retros. That poor old C-130 stopped dead in the air and dropped straight down to the runway. And that's kind of disastrous on the C-130s. Based on that, they said, okay, we believe you. Next time, we won't fire all 8. In fact, I think we had almost convinced them that they wanted to go back and fire them once they felt those wheels touch solid ground. So let's go ahead and we'll show the video. If you have any questions afterward, I'll try to answer them.
In early July 1980, the Department of Defense projected an urgent requirement for what has become known as the C-130 Super STOL aircraft. This requirement was for a vehicle capable of extremely short takeoff and landing distances with a large payload. It had to be capable of night, low-level, and tactical operations deep into hostile territory. Most importantly, this airplane had to be built in an extremely short time. The result of this program is the Super STOL, which can land and take off from a grass soccer field with 30,000 pounds of payload. In response to this requirement, a government industry team excelling in managerial, technical, and tactical expertise was assembled. The basic philosophy was to combine proven off-the-shelf technologies in new and unique ways, along with innovative management direction. Each member of the government industry team brought to the project unique expertise, which when integrated, made possible accomplishments not previously attainable until the 1990s. Even though the Air Force was tasked with the overall program management, a very important associate in this program is the Navy. The Navy at Dahlgren, Indian Head, China Lake, and Patuxent River provided experts in rocket propulsion and carrier operations. Mark 56 Standard missile motors were used for takeoff thrust augmentation. 8 Mark 56s, mounted in 2 quad pods, provided up to 180,000 pounds of thrust for 4 seconds, and 20 more seconds of sustaining thrust rated at over 20,000 pounds. These mount on the sides of the aircraft, on the pylon shown in this view. Shrike rocket motors are added under the wings, and ASROC rocket motors are used for stability and flight path vector control during takeoff. A unique application of rocketry was the use of retro rockets for landing. 8 forward-mounted ASROC motors provide over 80,000 pounds of decelerating force during landing. These, combined with 8 vertically mounted Shrike motors used to cushion the landing rates of sink, enable this vehicle to be landed and stopped in extremely short distances. Early in the design phase, a crash priority test program was conducted by the Naval Surface Weapons Center at Dahlgren, Virginia. These tests measured thrust, exhaust gas composition and temperatures, noise level, and rocket plume effects on aircraft structure. This crucial data was expedited to the Lockheed Georgia Company to begin the process of mating the rockets to the vehicle. An Air Force team was handpicked to interact in every facet of the operation. Drawing on gunship and pave-low expertise, as well as extensive C-130 R&D experience in Air Force Systems Command, a team was brought together including engineering, flight test, and management experts. From Tactical Airlift Command, Pacific Air Forces, and the United States Air Forces Europe came special operations crews with in-depth tactical expertise and knowledge. From Air Force Logistics Command, expert logisticians were brought aboard to speed the massive movement of required government-furnished equipment items. It became apparent that a very special and sophisticated avionics package would have to be assembled, integrated, and tested in order to enable this vehicle to achieve the necessary takeoff and landing trajectories, as well as the low-level tactical infiltration and escape portion of the required vehicle capability. Drawing extensively from pave-low, gunship, and combat Talon experiences, the Air Force assembled a group of expert government engineers and contractors to interface with Lockheed. Again, the philosophy of maximum use of available equipment employed in new and unique ways enabled the installation of the most sophisticated tactical STOL avionics suite to date in record time. From IBM in Owego, New York, came the central processing computer which orchestrates the cockpit. This was an adaptation of the pave-low, pave-tac computer with added software. Then from Texas Instruments in Dallas, Texas, came terrain-following, terrain-avoidance radar and a forward-looking infrared sensor FLIR with laser ranging. From Systems Research Laboratories in Dayton, Ohio, came fire control microprocessors, a STOL cathode ray tube symbol generator, and experience in avionics and electronic interfacing. Canadian Marconi in Montreal, Canada, provided a Doppler system which greatly increased navigational accuracy. Air Force avionics engineers from Wright-Patterson played a major role in bringing the system together and testing it in record time. The complete package includes dual redundant inertial navigation systems, advanced Doppler radar, terrain following, terrain avoidance radar, FLIR with a laser ranger designation, a Navstar GPS system, secure voice, and selected counter-threat devices. In addition to precision Doppler inertial navigation, with proven accuracy of better than 1/4 nautical miles per hour, the integrated avionics package provides internally generated terminal guidance displays to the pilots and crew to enable the vehicle to be flown and landed at night with precision using rocket assistance. Altitude, range, attitude, and steering commands are generated by the IBM computer and are displayed in real time on a CRT showing FLIR imagery, as well as on the modified Collins Attitude Director indicator. Preliminary concepts were completed by mid-August, and a contract with Lockheed Georgia Company was awarded on 19 August 1980. By 18 September 1980, the first test aircraft flew. This shows the airplane being modified from the C-130H to the Super STOL configuration. From the 1962 Rough Road Alpha tests, the C-130A was developed as a tactical transport. Other work done by Lockheed, including over 1,600 wind tunnel hours on C-130 STOL improvement and flight tests on C-130 boundary layer control, showed that Lockheed possessed a sizable engineering database which could be put to maximum use on this vehicle. Improved flight control systems included yaw damping, power control, and larger surfaces. STOL flaps with a movable aft section, new brakes, improved structure. Air refueling capability and an arresting hook system were also developed and applied to the C-130. The aerial refueling, for example, was borrowed from the C-141 stretch program. Testing of the Super STOL concept started almost immediately. As soon as the design was conceived, the Lockheed wind tunnel engineers went to work. Drag predictions, stability characteristics, rocket plume effects, as well as ground effects were studied in the Lockheed low-speed wind tunnel. Structural flutter tests were accomplished using the Georgia Tech wind tunnel. Extensive use of this data was made in the simulator. A research simulator was configured to investigate landing rocket firing sequences and to prepare the Air Force and Lockheed test pilots to fly this new vehicle.
Places us 500 feet above the terrain, 3/4 of a mile out from touchdown on a short field, 8 degrees of glide slope. We'll be approaching at 75 knots calibrated airspeed or 85 knots true. We will cross a 30-foot obstacle with 8 feet of clearance if we remain precisely on the glide slope. The aim point on the runway is the first black mark. The second black mark marks the end of the 600-foot landing zone, also noted by the scale C-130 model off the side. We'll begin the approach at this point. We're on localizer, on glide slope. Crossing 400 feet. 300 feet. 100 feet. Obstacle. You'll notice that the simulator visual system stops moving as soon as touchdown occurs. However, the teletype outside of the console will continue to print out the data that responds to our obstacle clearance conditions and our conditions at touchdown.
In order to speed the flight test program, a partially modified aircraft was used to test the ASROC decelerating systems, the wing-mounted Shrikes, and tail-mounted ASROCs, as well as the arresting hook systems, even before the first Super STOL rolled off the production line. On the 18th of September, the modified testbed made its first flight, and 2 days later, the first firing of retro rockets on conventional aircraft was made. Rocket firings were initially done on the ground in a build-up program to investigate their characteristics and interaction with the aircraft and its T-56 turboprop engines. Early in the program, methods of dealing with hot exhaust gases were found, noise and flame patterns were determined, and repeated maximum effect stops were made using all 8 ASROC deceleration motors. It was determined that the upper ASROCs could be safely fired even before touchdown, but that the lower ones must be used only on the ground. Testing progressed to the airborne firing of the pitch and yaw takeoff augmentation rockets. The pitch rockets consisted of 2 ASROC motors mounted under the beaver tail of the aircraft. They are nominally fired 4 seconds into the launch sequence to provide a pitch over correction during takeoff. Initially, they were mounted at a 25-degree angle, but as a result of these tests, were modified to a 12-degree angle for more controllability. The yaw and roll correction motors consisted of 2 Shrike rocket motors mounted on each wing pylon in place of the external fuel tank. These motors are sequenced automatically through the fire control system. If any 1 or 2 of the main Mark 56 takeoff thrusters should fail, an appropriate wing-mounted rocket fires automatically to correct the lateral flight path deviation. If no failure occurs, the motors are fired symmetrically for additional thrust. This sequence shows testing of the asymmetric correction system. Testing of the modified testbed aircraft continued with ground evaluations of the hook system. This was to be a tactical backup system using a lightweight, portable nylon energy absorber with 2 standard steel pendants. Several engagements were made on a dirt strip at speeds up to 80 knots. While the results of this effort were promising, certain technical problems were discovered which made the system impractical for the short-term requirement. Further testing of this system should be done in the follow-on program. All of the testing on the prototype was completed in less than 3 weeks. At the end of the 3-week period, the first fully modified XSC 130H Super STOL was finished and available for testing. In addition to the yaw, pitch, and deceleration motors, this vehicle had the Mark 56 takeoff thrusters and the 8 Shrike lift motors, the prototype STOL avionics suite, the STOL flap modification, the extended chord aileron, the horsels and dorsal fins, and several internal hydraulic, structural, and fuel system modifications. It was in effect a new air vehicle, far different from the C-130 that started mod only 6 weeks earlier. Testing proceeded rapidly on this vehicle. First flight airworthiness and flutter tests were made on the 17th of October, 1980. A destructive aileron buzz, flutter mode, was encountered on the first flight. Typical of the speed and dedication of the personnel on this program, a fix was engineered, fabricated, installed, and retested in flight successfully in only 2 days. The initial takeoff thruster firings were made on the ground during taxi tests using 2 motors, and then 1 motor, and the yaw correction systems. Airborne firings of the vertical motors were made both in and out of ground effect. Build-up tests on the XSC-130H prototype culminated in a record takeoff performance on 29 October 1980, which set a new record in tactical STOL operations. From brake release, the nose gear had reached 6 feet altitude prior to 10 feet of ground roll. The aircraft was airborne in 150 feet and was passing 30 feet of altitude and 115 knots within a total distance of 375 feet. The vehicle was stable and under complete control by the crew. It was on this same flight that an unfortunate accident occurred during the first fully Super STOL powered landing sequence. Due to a combination of circumstances, the horizontal retro rockets fired prematurely in the landing sequence, causing an excessively hard landing and loss of the first prototype vehicle. While certainly an unfortunate event in the progress of the C-130 Super STOL program, the loss of this aircraft provided impetus to improve and enhance the overall program. Due to the courage, skill, and dedication of the flight crew and ground personnel, there were no injuries and a major portion of the aircraft's equipment was salvageable. These tests have shown that rocket augmentation is a viable method of dramatically reducing field length. They were the culmination of an extensive cooperative effort between the Air Force, the Navy, and Lockheed over a 4-month period. More than 50 Air Force and 20 Navy personnel were involved together with some 1,000 Lockheed people. Over 850 engineering drawings were prepared. Some 400 wind tunnel test hours were used. There were numerous rocket test firings, and more than 900 hours of flight simulator time were used. In order to take advantage of and incorporate the many lessons learned in this program, it is clear that further work needs to be accomplished. To fully exploit the successes accomplished so far, and to test and develop the vehicle's entire spectrum of capabilities, more work is required in 3 areas: flight test and development of the existing Super STOL, researching improvements to it, and application of this technology to other missions or production aircraft. Future flight test programs will further define aerodynamic performance with and without rocket augmentation. Rocket control circuitry will be improved and reevaluated. Further avionics testing will be accomplished and the air refueling envelope will be determined. The goals of the proposed improvement program are reduced cockpit workload, improved flying qualities at low speed, improved performance on the ground and in the air, and improved airplane cargo capabilities. To reduce pilot workload and decrease touchdown dispersion, the avionics would be improved. An integrated autopilot flight director system would be added, and improvements made in cockpit controls and displays. Flying qualities could be improved at low speed by using a larger, fully powered elevator, a larger rudder, spoilers, and leading edge devices. Also, a modified aft flap actuation system could be used to provide less complexity and more reliability. Ground handling might be improved by modifying the nose gear steering. Cruise performance could be increased by modifying the ASROC fairings on the forward fuselage and by fairing of the vertical lift rockets. The third phase of future work, application to other missions or production aircraft, investigates application of this technology to production aircraft and to other C-130 versions. There may be innovative applications to assist the Marine Corps or the Navy for operation from ultra-short fields or aircraft carriers. Basic concepts have been proven. What remains now is to develop these concepts so that they can be applied.
Well, as you can see, that is different than your standard C-130. One of the reasons I think I got to called in, I'm a private pilot, and I did get to fly the C-130 simulator, and I did get to fly in the co-pilot seat on the C-130 when we were doing the tests, which was really spectacular. I'm single engine land, and boy, this is a big difference. So that was a real experience just in itself. Let's see, several other things. Back, I think I didn't bring out those. That was back in August or 18 September that we did that pretty much final all-up test. Those aircraft had to be modified because we were going to haul 100 Special Forces troops in that cargo bay, so they had to have restraints for 100 guys, all their gear, and then some extras for the hostages when they picked them up. Now, I don't know if any of you remember, but back when they started in originally with the choppers, they ended up moving those hostages and separated them. We had gotten some intelligence reports back within about 2 months that the hostages were all back where they originally started. In fact, they were being marched around this field that we were going to land in, the soccer field, and so they had pretty well determined that all the hostages were back where they originally started. And of course, that made our mission a much easier mission. Anyway, my comment is don't ever think that civil service job is just a ho-hum type job. You never know when you're going to be called to go do something that's really out of the ordinary. The biggest out of the ordinary is we were all going with them. Of course, we weren't at war with them back then, but they were taking a bunch of us civilians to this remote field in Turkey because we were going to arm that aircraft there. The other thing is the reason they put the in-flight refueling system on that aircraft is they were so concerned about leaking this, they were going to fly it nonstop from Dobbins Air Force Base to this remote field in Turkey with air refueling. They were afraid if they stopped anywhere along the way that it would get out that this strange aircraft was heading their way, and they didn't want that to happen. So a lot of things took place. We were supposed to go over in a C-141, be there. They were going to haul all the rocket motors over, and we were going to install them at this remote field in Turkey, and they were going to do the mission and come back. And then the hostages would fly back in the 141 with us. So a lot of really interesting things. A lot of us, we were even kind of sorry we didn't get to go try it because we think we had everything down pat by the time we got to that point. And it would have been a really exciting mission. Now, if you've got any questions, I'll try to answer them.
Did we give you hazard pay?
Probably, well, you know, no. I don't remember any extra pay, but I do know we were working 12 to 14 hours a day just to meet that time scale.
What's
Yeah.
the comp time?
Yes.
Or was it more than one aircraft?
Actually, when we were going to go over, there was going to be 2 aircrafts would have been completed. There was going to be 200 Special Forces troops on the ground in 2 aircraft, 100 in each aircraft. And then they would basically collect the hostages in that general area and bring them back to the aircraft. The one thing it didn't show you here is, of course, we were concerned about small arms fire. So we were in the process of putting some material over the rocket motors to keep small arms fire from penetrating. But again, didn't get to that total point, so we really weren't there. And when they finally canceled it and the hostages were released, but I think maybe it had slipped out that, hey, they were coming with something really big this time, so they, I think, gave up the hostages.
What were the G's on takeoff and stopping? And what are the pilots feeling in their seat?
You know, I talked to the pilot after that, both the Lockheed test pilot and the 2 Air Force pilots. They said they were absolutely amazed. Of course, they had full takeoff power on the turboprops when they fired the rocket motor. They said we just hung on and we could feel the acceleration, but it just kind of slowly pushed us down in our seat and we just held on. But he said the power came on really smooth. We were really surprised. Said we expected a real jolt, but it didn't happen that way.
And on stopping as well when they light off the arrestor rockets?
Well, that last one they probably had. Yes.
These guys, are the aircraft still at Davis-Monthan, or are they at the Air Force Museum?
The last I heard, they're at Eglin Air Force Base. No, they're not at Eglin. They're at Dobbins Air Force Base in Atlanta. At least one of them in their museum. Somebody told me that they were trying to get one of them taken back to the Smithsonian, but I don't know if that ever occurred. There was two aircraft after this one that got finished. Yes.
Who made the film, and what was the reason for the tailhook?
Well, that's an Air Force film, by the way. Air Force did all the video. They were thinking that initially they might drop some parachutists in. They would stake out a portable tailhook device. That just didn't make any sense at all. And they abandoned that pretty quickly. Well, they had enough rocket power that they didn't know what to do with it all anyway. Yes?
You never considered landing that thing on a carrier? Get them out, bring them on, drop them on a carrier?
As a matter of fact, that was one of the things they referred to in the video, is they think that would even be possible to land that on a carrier. Boy, I'm not sure I'd want to land it on a carrier, but
Jack Gately did it in the early 60s. He landed a fully loaded one and took off from the forest hall.
so,
Several times.
well, that would be interesting. Now, probably with JATOs, right?
No,
No?
fully loaded, no arresting gear, landed on the forest hall, came to a stop midships and took off. There's some video of it.
That's interesting. So, well, in most cases, that's really hard. And, you know, I guess if you have enough headwind to really, you know, you're really, when you flare it, you're slowing pretty slow, I think you could do that. But if you didn't have, and of course they turn those carriers into the wind when they're going to land. So that might be possible. Right there at the last where they fired all 8 in the air, I was in the fire, they put us engineers in the fire trucks on each side because we had to make sure that the rocket motors weren't acting like they were getting ready to fire. You sure don't want to pull a fire truck up and have a rocket motor go off. It would ruin your whole day. So they had us engineers on the fire trucks on each side.
In the video footage, you can see what looks like a little parachute tailing behind the aircraft. Is that a tethered?
I suspect something for measuring airspeed or something. I would guess. Yeah, I saw that too. So.
Well, what was the heat like inside of the airplane when all those rockets went off?
Amazingly enough, not much inside. But like I said, everything was, you know, they're moving pretty fast through the heat plume. The biggest thing is the tail assembly from those side rockets was getting all that heat right up into the tail assembly, and but just a little insulation on that tail assembly got us through that 4-second boost phase without any problems. Yes?
Pilots had a look at that gauge in the center to judge their approach at night.
The FLIR, forward-looking infrared, yeah, it's a screen, and you could see what looked like light-colored images, and that's basically what they were going to land with at night on that field. You saw how short that looked from that first line to where they had that aircraft. That's basically the length of the soccer field, and it's awful short. I did several landings in the simulator with that, and boy, I tell you, you better hit it right on the nose. And of course, those pilots were really good. They had 2 outstanding Air Force pilots, and of course, Lockheed's test pilot is just outstanding all the time. Well, he does a lot of that, so he's real familiar with the C-130. Okay, if there's no other questions, thank you for coming, and hopefully you'll find a job that'll be just as exciting, and hey, don't turn it down. You don't know how good it might be.
Okay, thank you, Mr. Renner. Lou? I have a certificate for you to thank you for the stories today, and one of our highly coveted full-size posters that you can take home.
Thank you.
Thank you.